Okay, hi. Um, this is a video lesson on Newton's three laws of motion, and I'll be covering some mathematical concepts, mostly in the second law. And the first law is pretty intuitive. Same with the third law. Well, not intuitive, but really not much mathematical concepts. And before that, I'll be introducing forces and motion. And if you're just a regular viewer, feel free to check out some of my other tutorial videos. And I'm actually doing this for a project, so if you're a viewer from school, then you have to check out my other videos. I am forcing you. I am anti-democratic. Okay, so we are going to start out by, what color should I use? Forces and motion. Motion. And I don't have a tablet, so I can't write this good. But so I apologize for the messiness. Forces and motion. Well, I think it would be a good place to start out by asking, what is a force? What is a force? The simple answer most of you will know is force is, or put it this way, force is a push or a pull. So, if there was this block here, if a stick figure had some rope and was pulling it, that is a force. Or if our stick figure was pushing it, that would also be a force. If it was pushing it. Like that. Okay? Next. Our next thingy, motion. So what is motion? Motion is, and the simple answer is a word that is synonymous to motion, which is, I will use this color. Motion is movement. Force is a push or pull, and motion is movement. So what is movement? Movement I'll just put a dot and abbreviate that. Movement, well, where does movement come from? Movement comes from a force. So we are going back to our first definition of a force. Movement comes from a force. And a force, with our stickman example before, if this stickman was moving this block, it's pushing this block with some force, let's call it X. So the stickman is only moving this block because the force X is strong enough to move the block. If the force X was not strong enough to move the block, for example, if the block was heavier or something, then the force X may not be strong enough to move the block. So forces can only move stuff when the block or whatever it's moving is light enough or this force is strong enough. So, this comes to a question. If we can't move some objects, why can't we move these objects? And this, my friend, is a thing called inertia, which I will explain in a few seconds. And I have my inefficient way of erasing all this. Okay. I will erase this. Oh god. Or I will reopen paint and then good. I am pleased. Okay, so inertia. It's this strange thing that will explain all our problems. I hope. So inertia. Inertia. So I will explain inertia. If I have our famous wooden block example again on this table. What does this wooden block want to do? The answer is simple. The block wants to stay at rest. So, if it didn't want to stay at rest, then the block would be flying around randomly. Yeah, so the block wants to stay at rest because it is lazy. So it wants to do what it was doing before. So this is actually Newton's part of Newton's first law. Newton's first law says that an object at rest will stay at rest, right? Like this block is going to stay at rest. It doesn't move anywhere. And an object in motion will stay in motion. So we will erase all this. So an object at rest will stay at rest. But if this block was not a block and it was a car or something, say our block was a car. It's on this table again. Actually, I don't like that. Let's see. It's on this piece of ground, and the block is moving this way really fast. So, if this person is here, and then the car collides into the person, bam! Person is not happy. Okay, whatever. Okay, so what will happen to the person? The person will probably get squished, and this car will probably keep trying to move. Move this way. This way, way over there. So the car tries to keep going there. But this does not seem to be true in our everyday experiences. For example, if our famous example from Khan Academy. So if Newton came up to me and said, I've discovered this amazing law, and it says that an object at rest will stay at rest. So that's Newton with a hat or something. So I say, Newton, that law isn't true. Look, if I'm holding this apple, I have this apple that looks like a cherry. If I'm holding this apple, and it's just there, and this is the ground, that's my hand, but it's badly drawn. I'm holding this apple, and the apple isn't moving. And then if I just let go of it, why does it drop? And, well, Newton is, like, I didn't push it, I didn't pull it, I didn't apply any force on it. So why does it drop? And Newton's obviously going to say it's because of gravity. and I will tell him that you're making up stuff, but as Sal says in his Khan Academy video, eventually he'd be right. And I will tell you more about inertia in my next video, because I'm out of time. Thank you for watching. Go to my channel and check my next video out. Bye. Hi, welcome back to my video series on Newton's 3 laws. And on the previous video, we left off on the first law, which, if you didn't realize, is the law of inertia. So, just to review, the law of inertia says that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by an external force. So, before we had our stick figure example, our block example, where we have this wooden block, and the block wants to stay at rest. But if, for example, a human pushed the block with his or her hand, pushed it, then the block would be forced to move unless the person was a weakling and they couldn't move a block. And we had our example with an apple, and how an apple at rest would drop if you just let go and you had no force on it. But this is because of the force of gravity. So gravity was actually pulling down on it. And then we had the force of our car. The example of a car that was moving and how the car wanted to keep moving. And I'll also say that, I will also say that if, for example, there was a wall that blocked the car, some wall here, and I'll erase that Newton, that man who's blocking our wall, sort of, later. But if there was a wall, the car is forced to stop unless the car has enough force to knock down or break the wall or something. So it's because the car is being acted upon by the force of the wall. And I'll explain why a non-moving object has a force on the car in Newton's third law. So I will erase all this. Okay, good. So that is the law of inertia. An object at rest will stay at rest, and an object at motion will stay in motion unless acted upon by an external force. And one more thing, an object in motion will stay in motion, so this car will stay in motion. Oh, actually, two more things. This car will stay in motion in a straight line, exactly straight, until acted upon by a force. So if this brick wall was here, it would go straight until it hit the brick wall, or well, there's friction on the ground, so that's why things that go flying don't go straight all the time in our world. And this leads to another thing. Inertia doesn't always seem to work in our world. With an object at rest will stay at rest. I had the dropping an apple example. And I'll just write apple there. Apple. Okay. And then we also have our let's see. So an object in motion will stay in motion unless acted upon by an external force. So, for example, our car. If we had a toy car and we pushed it forward, the car doesn't go forward forever. But an object in motion is supposed to stay in motion. And this is because of the force of friction. So it's just, but in space, in deep space, where there's no friction, no outside forces, if there's no nearby planets, then these laws would work perfectly. Like if you threw a toy car into outer space, it would go straight forever in deep space. So that's the law of inertia. Next, I will be moving on to one of the most mathematical law of the three laws, which is Newton's second law of motion. And I need to check here if I've got any time left. Okay, whatever. Newton's second law of motion is Newton's second law. Just put it like that. Or actually, I prefer Newton's second law. This describes the relationship between force, mass, and acceleration. Force, mass, and acceleration. So earlier we learned that force is a push, or a pull. Mass, we come to mass. Now, we're soon gonna learn that there's a difference between mass and weight. Mass and weight, there's a difference. And we will also learn about acceleration, and we will find out that there is a difference between acceleration and whatever. We'll learn about acceleration, velocity, and speed, because we'll need those in some other videos, and we will discuss the units used for acceleration, velocity, seconds, meters, weight, force, etc. Units. That's one of the most fun parts of this. And then we will, yeah, that's basically it. So we'll learn all of this in the next video. So see you soon in the next video. Okay, welcome back to my Newton's 3 Laws tutorial video, or whatever you want to call it. Internet video classroom, or whatever. So, if you haven't watched the previous video, go to my channel, or if you see it at the side, or whatever, just watch the previous 2 videos. This is part 3 of my series. Please watch my previous videos and you'll probably understand a lot more stuff. Yeah. So in my previous video, I said I was going to teach you about, well, we already learned what force was, a push or pull. And by the way, we're learning Newton's second law. And I'm going to teach you the difference between mass and weight, and stuff about acceleration, velocity, and speed. Okay, I'll just keep that in mind. And then I'll teach you some units for force, mass, and acceleration. Okay, good. So first, on to the difference between mass and weight. What is the difference between mass and weight? Well, in normal life, people use the two interchangeably, but actually, in physics, we must be smart. And mass. Mass is how much of an object you have. So, you have, for example, 5 kilograms of chocolate pudding. That's mass. Something I'm abbreviating. Something you have. Something you have. How much of something you have. Okay, and on the other side, weight, on the other hand, weight is the the force of gravity on a certain object or any object. The force of gravity on an object. So, the mass of chocolate pie, some chocolate pie would be the same on the moon and the earth, or on Jupiter and the earth. But the weight would be different because the gravity on Jupiter, I'm pretty sure, is different from the force, the amount, the strength of the gravity on Jupiter is different from the strength of the gravity on Earth. And gravity is a force, so yeah. So weight depends on how strong gravity is, while mass never changes. Mass is a constant. So and by the way, if you don't understand any of this, feel free to comment if you feel that everyone who views this video should would benefit from your comment. And if you don't feel that way, you can also PM me, personal message me. I respond to all messages as quick as possible, or I try my best. So, yeah. Let me erase this. Yay. Paint is being nice to me today. No, it is not. Oh, yeah. Okay, I'll just erase a little. Okay. Thank you, Paint. So, on to acceleration, velocity, and speed. First, we will discuss the difference between velocity and speed. Velocity and speed. Okay, so what is our difference here? Well, for one thing, our velocity here, velocity is, well, both, first of all, are the derivative of the rate plot, which means basically the change in the rate plot. Okay? But velocity is a vector while speed is a scalar, which means that speed is just is just a magnitude, and you probably have no idea what I'm talking about. And velocity is a magnitude and direction. So, for example, speed would be 10 meters per second, while velocity is 10 meters per second west. 10 meters per second west. So velocity tells you the direction you're going and the speed, while speed only tells you how fast you're going. So that's the difference between velocity and speed. And I usually find velocity to be a little nicer because you can specify where you're going. Okay. So now I should be explaining acceleration. Acceleration. This is one of those terms people don't understand. They just see it in like Mario Kart or something and assume it's the same thing as speed or velocity. And that is, again, a no-no. Acceleration is is the derivative or change in speed, if I remember correctly. Change in speed in change in speed. So, I must check my time and see if I am running late. Oh no. I have 2 minutes left, I think. So, acceleration is a change in speed. And, anyway, acceleration is the change in speed. So, the formula or whatever for finding acceleration is acceleration equals, I'll make this bigger actually, and this formatting got messed up, so never mind. But, acceleration, I don't like this. Acceleration, no, I do not like this either. Acceleration equals, do I remember this right? Okay, so I have a site here. Final velocity. So, final velocity and with a subscript f minus the initial velocity divided by time. And this can be written as seen here, like this, which equals triangle thingy velocity divided by time. So this means if we have this, let's do a problem with this. So if our person here, if this person, let's say this person is accelerating at 5 o'clock, 0 seconds. So just 5 o'clock at a speed of 0 meters per second. So at 5 o'clock and 5 seconds, the person is accelerating. Well, not accelerating. The person, let us say, is not moving. Let's just say that. And then at 5 o'clock, I look away, and then 5 seconds later, 5 o'clock and 5 seconds. 5 seconds. Okay. At 5 o'clock and 5 seconds, the person is accelerating at, let's say, 10 meters per second. Sorry. At 5 o'clock and 5 seconds, the person's speed, velocity, is 0 meters per second. So the person is not moving. And then at 5 o'clock and 5 seconds, at 5 seconds later, the person's velocity is 10 meters per second. So let's plug our numbers in. And I need to move this somehow. What shall I do? Okay, I will just do this. So let's just remember that at 5 o'clock and 5 seconds, the person's velocity was 10 meters per second. Yes. Thank you. And this A and C are not cooperating with me, so I shall demolish it. Thank you. That's good enough. Okay, so at 5 o'clock, I'll just write it like that. The person is accelerating, sorry, the person's velocity is 0 meters per second, and I won't make velocity into a vector. Let's just pretend it's speed, but velocity sounds better. So in some direction, actually velocity matters, but in some direction, we don't really care about the direction right now. And then 5 seconds later, at 5 o'clock, and 5 seconds later, the person is velocity is 10 meters per second. 10 meters per second. So, how do we solve this? Let us look at our this thing again. So, acceleration equals final velocity minus initial velocity divided by time. So, our final velocity, let's just put this over time. Okay. No, I don't like that. So, our final velocity was 10 meters per second. Final velocity. And actually, I'll circle that in red. And then write it in red here. So 10 meters. And I'm not sure if you can see this, so I'll zoom in after. But 10 meters per second. And then our initial velocity, which I will circle in blue. So 10 meters per second minus 0 meters in, no, that's not the right color. Thank you. Minus 0 meters per second divided by the time. So if we subtract 5 hours and 5 seconds from 5 hours, we get 5 seconds, which I will circle in a different color. 5 seconds. So, divided by 5 seconds should equal the acceleration. So, let's do some math. 10 meters per second minus 0 equals 10 meters per second. Because, let me think. Yes, 10 meters per second. Actually, this may or may not be correct, but the meters, I'm pretty sure, I'm a noob at this, but the meters per second minus a meter per second cancels it out. So, no, I'm being stupid. Okay. 10 meters per second, because it's 10 minus 0, divided by 5 seconds. So, we divide 10 by 5, because, obviously, a fraction is the same thing as dividing, and we can simplify the units later. So, we divide by 5, and we get 2 meters per second divided by another second. And this, this is the reason that acceleration, which I will show you soon, is written in meters per second squared. So the answer to this question would be 2 meters per second squared. And you may ask why this happens, but this is because, I will write this here again. This is exactly the same thing as, I'm trying to make this a little intuitive, but exactly the same as 2 meters per second, and then the thing in the denominator, slash second. So, and then the squared here signals that there are 2 seconds instead of 1 second. So there is our acceleration problem. I'll just pause this or something. Welcome back, everyone. And in the previous video, we may or may not, well, in the previous part of the video, or doesn't, if you're viewing it on YouTube, the previous video, we did some acceleration stuff. And now we did the difference between mass and weight, and I'm pretty sure of a previous video. And now we are going to do, well, we're going to get back on track with Newton's second law, which is force equals ma, mass times acceleration. And this is just algebra notation. So it's force equals mass times acceleration. Okay. Yep. So, yeah, if I don't remember if I did this before, but we need to use, if the acceleration was 2 and the mass was 5 or something, the force would be 10. But we need to use units when we are calculating things, because one could not say that they had 5 waters. They'd have to say they had 5 liters or 5 millimeters of water. So then, in physics, we traditionally use the metric system because it tends to make more sense. So traditionally, we use kilograms for mass, and we use meters per second squared for acceleration. Did I cover that in the previous video? I'll just check. I'm sorry. I will check if that I covered that in the previous video and come back. Yay, I am pleased. I did not cover this in any previous video, so this is new stuff. Anyways, so we use meters per second squared for acceleration. And then the question is, for force, what do we use? Oh no, wait. I will pause again. Aha, I am pleased again. I covered also why acceleration is meters per second squared. So we can get onto force. So the big question is, we know the units for mass and acceleration. What is the unit for force? And the answer, my friend, is we use a unit. I will use purple. Oh no, that is not purple. We use a unit called newtons. And this is in the honor of Newton himself. And it's abbreviated with capital letter N. Newtons. So, what does a newton, how do we measure newtons? What does a newton equal? Well, the answer is right in front of your face. Excuse me. Here. So, acceleration is meters. Sorry. Acceleration is meters per second squared. It basically equals meters per second squared. Just think of it like that. Meters equals kilograms. Force equals newtons, right? So, this law above is telling us is that if we plug in the numbers like this, multiply mass and acceleration, we get our force. So all we do, these equal each other. So we just replace it so that it says, instead of force, it says newtons. Newtons equals, instead of mass, it says kilograms. Kilograms. And then, instead of meters per second squared, kilograms times, and the dot is a time sign, meters, whoa, per second squared. Meters per second squared. Meters per second squared. Okay, so this means that 1 Newton equals 1 kilogram. And I'll use a different color so it looks less confusing. Times 1 meter per second squared. 1 Newton equals 1 kilogram times 1 meter per second squared. But eventually the ones cancel out because 1 times a number or something is the number or whatever you multiplied. So 1 Newton, the force of 1 Newton would, an object that is flying would have a force of 1 Newton if it weighed 1 kilogram and it was going at a speed of, an acceleration of 1 meter per second squared. In the same way, an object that's 2 newtons might be, and there's lots of possibilities, but 2 kilograms times 1 meter per second squared. So I hope that I explained that pretty intuitively. So on to more complicated problems. And this system seems to be shutting down in 14 minutes and some seconds, so I better hurry up. So if we have F equals ma, we also have to draw a conclusion that A equals F divided by M, because if we flip the equation, then it becomes like this. And M equals F divided by A. So this is, in my opinion, where problems get a little harder. Oh no. This seems to not be cooperating. Haha, I shall close this window and restart Paint. So anyways, I will write down our equations. I will write down our equations. A equals Fm, F divided by M, while mass equals F divided by A. So, I will explain this in the next part of this video series. Bye-bye. So, back to our two equations here. A acceleration equals force divided by mass, and mass equals force divided by acceleration, which originates from force equals mass times acceleration. So in my opinion, these two things are where things get a little fun and more complicated. So let's say our acceleration is 10 meters per second squared. And one of those Toshiba PC annoying health monitor things popped up, but ignore that. And 10 meters per second squared, and the force is, or actually, I am sorry, let us do this without knowing the acceleration. So let's say our acceleration, we don't know what our acceleration is, and let's say our force equals 15 newtons. 15. Or we could actually put this into real life, and there is an object that is 5 kilograms. Its mass is 5 kilograms, and the force, it's moving, and it's a baseball, and it's moving at a force of 15 newtons, and it's 5 kilograms. So what is its acceleration? Or, yeah. So, uh, we solve this problem. I will erase the mass thingy first, because that's more important. Because we need more space to learn this. And I am magically erasing the equation using a paintbrush. So, I expect to be done in the next 5 minutes. Oh yeah, I just realized I could pause this and not waste so much time, but I'm dumb. So, anyways, let's write this out again in a nice color called blue. Acceleration. I like this color because it makes me happy. Okay, acceleration equals 15 newtons over 5 kilograms. Maybe I will make the 5 kilograms a different color for no apparent reason. Because let's just say I like the color yellow. And it makes it look prettier. So the acceleration equals 15 newtons over 5 kilograms. So we first expand um, the the fraction by expanding the term called newtons, and I'll put that in red. So 1 newton, we saw in the previous video that it equals a meter per second squared times a kilogram. And as we can see, we have a kilogram here at the bottom and a kilogram at the top. So the kilogram at the top will obviously get cancelled out by the kilogram at the bottom, because one thing divided by the same thing is 1, and 1 times anything is the number. So we now have 15 meters per second squared, and then the kilograms at the top and bottom canceled out, so we just have 5 at the bottom. And then what we just do now is divide 15 and 5. We don't worry about the units yet. 15 and 5, and we get 3 at the top, and then there's nothing left at the bottom because the 5 is now already divided the 15. So we get 3, and then the meters per second squared is still there. Meters per second squared. So this is our final answer. The acceleration of this acceleration of the ball is 3 meters per second squared, and we can check that by multiplying with acceleration and see if we get the force, because mass times acceleration is force. So we multiply it, 3 meters per second squared times 5 kilograms. So the kilogram and the meter per second squared equals a newton, right? So those two multiplied is 1 newton. And then the 3 and the 5 multiplied equals 15. It equals 15. So we have an answer of 15 newtons. And I hope that was pretty easy. And I was explaining it well. Maybe not. But, okay. I have officially 3 minutes left. So I will pause this and erase everything. So now we have our equation, our other equation, m equals f divided by a. Mass equals force divided by acceleration. And this is actually almost the exact same thing as acceleration equals force divided by mass. So let's say our ball, this time we have another ball which is traveling at a force of 20 newtons. I am sorry, that is a bad zero. 20 newtons. M equals 20 newtons. And then its acceleration is, let's say, 2 meters per second squared. Actually, this might be a little more intuitive if I put it in a different color. So 2 meters per second squared. And then we have to find out the mass. So we'll write that here. M equals, we put it into fraction form, 20 newtons over 2 meters per second squared. So we expand the fraction again, and we get, because Newton equals a kilogram times a meter per second squared. And actually the kilogram and the meters per second squared, doesn't matter what order you write it in, but kilograms times meter per second squared over over 2 meters per second squared, and then this cancels out to become, because there's meters per second squared at the top and at the top and the bottom, so those two cancel out, as with the kilogram in the previous example was A equals FM. So 20 kilograms, and then times meters per second squared cancels out because it's also right here. It's there and here. It's in both places. So that cancels out, so we only have 20 kilograms over 2, because our meter per second squared here canceled out from dividing the one at the top. And that equals, now we just do regular division, and 20 divided by 2 equals 10, and then our unit just remains the same. So our mass equals 10 kilograms. We have solved for mass. And again, we can check that by multiplying our mass here and our acceleration here. So 10 times 2 is 20, and that is our force. And a kilogram times a meter per second squared is 1 newton. So we'll write it like this: 10 times 2 bracket plus, I'm like out of time now, but wait, kilograms times meter per second squared. And I may or may not zoom into this, but which equals, wait, I'll pause. Okay, I'm back. So anyways, that equals, which equals 10 times 2 is 20, plus a kilogram times a meter per second squared is a newton, which equals 20 newtons, which is our force right here. So I'll see you in the next video, because I'm trying to keep my videos under 10 minutes, although I do have, my account has been enabled for videos over 15 minutes. So, thank you and bye. Welcome back. And I'm sort of in a bad mood right now because I just spent about 20 minutes making the last part or the second last part of this video series, and it got deleted. Well, no, I closed my video screen recorder before it processed the file. So, yeah. So I'm starting again. And this is I'm on Newton's third law. Newton's third law. And this is zoomed in too much. Good. Newton's third law of motion. I'll just write that to look fancy, make it look fancy and make me look professional. Anyways, Newton's third law states that, and I will type this, for every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. So this tells us that if I were to have my hand here, a badly drawn hand, and push out this wall, if I were to push out this wall with a force of 10 newtons, the wall would push back at a force of 10 newtons. And this doesn't seem to be true in real life, because if I actually go and push a heavy brick wall, then the wall, I'm gonna get pushed back, right? But this is because the brick wall is way heavier, while your hand is very light compared to the brick wall. And I will try to make this intuitive, but like easy to understand. But this also took me a long time to comprehend, so don't be discouraged if you don't. Anyways, let's make another example. This is one of the most common, well, a very common, I can tell you that, example. I am standing here on the ground, and the ground is, well, if the ground, well, I'm pushing down on the ground for one, because gravity is pulling me down, and that is a force. And in response, the ground is pushing up at me. If the ground wasn't pushing up, I'd fall through the ground and die. Another thing is gravity is pulling down on me. And the conclusion, and this is really cool, so I'll put it in blue because blue is a cool color. If gravity is pulling down on me, I have to pull up on the earth, which is cool because right now you're sitting here at the computer and you're actually pulling the earth up, because if gravity is pulling you down. But when people like this gets 5 million views on YouTube, and in 20 years or something, and people live on the moon or something, or somewhere that there's no gravity, this might not be true, but for now it is. Anyways, let me see. Another example, and by the way, the forces of you pulling up and gravity pulling down is equal, so you're as strong as gravity. And the force of you pushing down and the earth pushing up is also equal. Now you might say Newton's third law doesn't work because, for example, this little bug, let's say this is a bug, I don't know what type of bug, but it's a bug. And then this is your shoe. This is someone's shoe. And then their leg, right? And their shoe is pushing down on the bug. And the bug gets squashed, and it feels like the bug has no resistance. But actually, if you were to push down with your shoe at a force of 9,000 newtons, and that's a pretty good force for a shoe, the bug would push up at a force of 9,000 newtons. Why? Because the bug has guts, and mass is way more smaller, which gives you an advantage for because with the same force, different things can happen. For example, if you were trying to move a construction truck, if you applied 100 newtons, like 2 newtons to it, it might not move it. But if you applied 2 newtons to a tiny rubber ball, then it would probably move it. So the point is, the bug has the same force, but under certain circumstances, the same force can have different effects. So that's actually probably my shortest lesson for a law. But now I'll do some problems. Okay, I'm back with some problems. So, let's say our problem for Newton's third law is that, there is a fly. And this is our fly here. Those are its wings. It doesn't look like a fly, but trust me, it is a fly. Maybe I'll make the fly a little bigger. So I'll draw over the wings, and here are its new wings. Anyways, that looks like Mickey Mouse. But the fly is flying towards this direction, and there, unfortunately for the fly, there is this giant bus, school bus or something, also traveling in the opposite direction of the fly, a school bus. And let me color in the school bus so it looks prettier. Yeah. The school bus is not cooperating. Anyways. So, I will color this in. Good. Yay. So, the bus is traveling towards the fly. The fly and the bus suddenly collide with each other, and the fly slides into the bus at a force of 10 newtons. At a force of 10 newtons. So the problem is, and the fly is crashes into the window of the bus and makes a mess. Blood splattered everywhere. Sorry if you're uncomfortable with that word, but anyways, so the fly is dead. It's squished, and the bus just keeps moving like normal. What is the force of the bus on the fly? And you can pause the video if you don't want to, you want time to figure it out. But, well, pause it now if you want to. Okay, so the answer is the force of the bus on the fly, I'll put it in red, is equal, because for every action, which is the fly crashing into the bus, there is an equal and opposite reaction. So the bus's reaction, the force is equal. So the force of the bus is 10 newtons. And some might question this and say that why the fly got owned by the bus, or I'm lacking the use of a more formal tone, but why the fly died from the bus, or why the fly got squished by the bus, I do not really have a preference, but this is because the fly, as I mentioned before, has guts, and guts are splatterable, while the bus doesn't have guts. And also, the fly has a much smaller mass than the bus, and less mass means less momentum, because which is a factor in this, I guess, because momentum equals mass times velocity. So you can see that similar to force, which is mass times acceleration. But anyways, that's the end of my third law video. check out my other lesson videos, feel free to do that. Thanks for watching. Bye.